Hi there, and welcome to this webinar on pipe stress analysis. My name is Matthew Ford, and what we're going to look at today is using SolidWorks Simulation to analyse pipe stresses or stresses in pipe systems following the more conventional system of pipe analysis as opposed to just using standard solid meshes and ascertaining what the von Mises stress is. Hopefully that will become a bit more clear in a moment. Okay, so just a quick look at a brief sort of standard requirement, so something we might see from, say, the ASME code or anything like that. So what we might see, for example, is what you've got on the screen here, so perhaps a longitudinal stress due to the pressure inside the pipe and the weight of the pipe itself, so just force due to gravity, no more than 131.2 megapascals. Do note that these aren't actual values that I've drawn from the ASME code. These sorts of things do change all the time, and it's sometimes quite difficult to get hold of the codes and standards. What I've done here is just sort of take some sort of rough general values based on what I've seen in the past. Again, we've got another one here, the longitudinal stress due to full liberal displacement stress range. So let's talk, say, shifting one of the ports on one of the junctions up and across or something like that, and we will actually be doing that in a moment. The maximum allowable stress there, 298.4 megapascals. Finally, a longitudinal stress due to occasional load. This may well just be perhaps a wind load or something like that, so a force acting on the side of the pipe, 187.9 megapascals. So these are the sorts of things that we might be looking to draw a comparison with when we actually get results from our studies in SolidWorks Simulation. I will draw your attention to the fact, and this is written in bright red across the bottom here, that this isn't a certified analysis process. There are specific tools, other pieces of software that will give you certified results. The idea is here that we can draw a comparison during the design process with some of these standards and these codes, just to guide us as we design and as we choose what we do with our geometry in the setup process, as opposed to just analysing at the end with a full package. Okay, so don't try and use this tool, for example, to qualify your geometry or your designs to align with the code. That's certainly not what this is for at all. Okay, so let's now go ahead and have a look at the model. So what I've got here is a very simple model. I've got a couple of flanges at either end and the pipe obviously routing in between. Now this is a piece of geometry that has been generated using the SolidWorks piping and routing functionality. So you'll see we've got the icons here, and these have been nicely sorted into root parts and components. I'm not going to show you how to set that up. That will be for a different webinar. Instead, what I'm going to do here is use the simulation tools to analyse the geometry that we've already produced. Okay, so the first thing I want to draw to your attention is the way in which the geometry is being produced. So if I just take a section and have a look at this, you'll see that we've got a pipe that has been generated. So it's a three-dimensional pipe. It's got a thickness in here, and that thickness is obviously going to carry on throughout the geometry. The key area of interest is this region here. So you'll see where we've got the flange attached to the pipe, we have just got this cutout here, which would be where the weld bead would go. So we're going to have to deal with that pretty specially, because we've just got essentially an edge-to-edge contact there. We're not too happy about the way that bond is being executed. So we'll have to be very careful when we come to that in the analysis. Because we have got a very long and slender geometry, so we've got a thin wall thickness, and we've got large dimensions in the other two directions, I'm going to take a slightly different approach to just using a standard three-dimensional mesh. So instead what I'm going to do is use a two-dimensional mesh, or a shell mesh. Hopefully, if you've been catching up on previous videos, you'll be aware of what that is now. So what I'm going to do beforehand, just a bit of pre-processing, is generate a surface body so I can negate this solid pipe now from the get-go, and then SolidWorks will be up and running, ready to go from there. So I'm going to switch to my surfaces toolbar. First of all, creating a new part. Okay. And I'm going to edit that part and switch to my surfaces toolbar. There he is. And what I'm going to do is use the offset surface command and I'm going to select all of the faces that we've got in there. So I've just right clicked, gone to select tangency, and you see that's gone all the way through the inside of that pipe. I've been careful to grab the inside of that pipe because that's the surface that is in contact with the flange. It just makes things a little bit easier later on. And then what I'm going to do is specify what thickness this pipe is. No, I'm not. Sorry, that's another time. What I'm going to do is offset by a value of 0. So now we've got another surface at the internal location of that pipe. So if I go ahead and suppress that pipe section, you'll see that now we've just got that surface body in there and ready to go. Okay? What I'm also going to do is just briefly have a look at my numbering scheme. So the way I've done this is I've just set up and told myself that I'm going to analyse the pipe sections in this order. So we've got section 1 is this straight section here, section 2 is this bent section or this elbow here, 3, 4, 5, 6 and 7. Okay, now that will come to light in a short moment. So what we're going to do is analyse each of the individual pieces as we go. So now what I'm going to do is go ahead and create a new study. So up to my simulation tab and create a new study. Let's just call this one displacement. So this is the one where I'm going to drag my flange over across in a specific direction. So I'm just going to call that a displacement study. And then in here you'll see I've got 2 solid bodies and that shell body. So that's the body that we're using to represent our pipe. So the first thing for us to do is go ahead and apply our material. So I'm going to right click here, apply material, and in this case I'm just going to use a plain carbon steel for everything, just to keep it nice and simple, like so. So you see we've got green ticks on everything, we've got plain carbon steel applied to everything. Next I need to tell SolidWorks what thickness this sheet is. So in here I'm going to select thick, and what that's going to do is allow me to make sure that I'm analysing not just the bending stress and the membrane stress in our geometry, but I'm also able to analyse the shear stress, so the stress through the thickness of the pipe section there. And that's important because that's something that would be overlooked if we do select the fin. So in here I've got a 3.9mm wall thickness, and in this case I'm going to tell SolidWorks that I have selected the bottom. So SolidWorks is going to extrapolate the thickness of the pipe outwards. It knows that I've selected an extremity of the geometry as opposed to a mid-surface, a surface that's going through the middle of the thickness everywhere. Okay, hit OK, and that's SolidWorks ready to analyse those parts. So next what we need to do is set up how we want them to interact by going into the components contacts. So here we've got a global contact, and what this is going to do is select or apply the bonded contact to any 2 bodies that are in a surface-to-surface contact at the beginning of the study. We haven't actually got any of that here because, as I said earlier, what we've got in here is an edge-to-face contact or an edge-to-edge contact, which means that we're going to have to specify our own manual component contact to override that. So I'm going to select the contact set in here and come in and grab this bonded option. I'm going to pin it just so that it doesn't disappear when I hit the tick. That just allows me to do 2 contacts quickly. I'm going to grab that edge on this body. I'm going to grab that face on the flange and hit OK. So I'm just hitting my right mouse button to select OK. I'm going to do the same up here. And now we've got that bond set up. You'll see we've now got an additional folder with 2 bonded contacts applied. Okay, I think what I might just do now is turn off my annotations just so that they're out of the way, and the next thing we're going to do is apply our fixtures. So this is how we're going to constrain the movement of our geometry to stop things flying off into the distance when we apply a load, and also to tell SolidWorks how we want to move one of these flanges. So first of all I'm going to right click on the fixtures and come in and use a fixed hinge. So this one is what I'm going to use to constrain the movement of these components here. So of this component, so of the flange. So this hinge is only allowing rotation about that cylindrical face. So if we consider this particular face, for example, let's imagine an axis going down the middle of the cylindrical face. We can rotate about that face, but we can't translate along it or away in the radial direction. Now, because we've got 4 of those on there, if we rotate around this guy, that would involve radially moving one of these, so that's not going to happen. So what we've done is constrain the movement of our geometry quite well, without adding too many or without restricting too many degrees of freedom. Because if we do restrict too many degrees of freedom, what we can actually do is start introducing our own errors, because we're not allowing geometry, or we're not allowing areas to move as they want to. Okay, so I'm going to hit the green tick there, and that's applied my fixed hinge to those 4 holes. And then what I'm going to do is come up and apply my displacement to the other 4 holes. So I'm going to use the advanced fixture here, and I'm going to grab these 4 faces in here, like so. And for my reference, I'm just going to grab my front plane. Then down here what we can do is specify which specific translations we're after. So I've got, in this case, I'm just going to stick something like 2 millimeters on here, and for this one I'm going to shift it by 5 millimeters in the negative direction. So we're going down to, we're going across 2 and down by 5 millimeters. So we can hit the green tick on that one, that's just fine. So we've got our displacement set up. Finally, all we need to do is specify our mesh, because we haven't got any additional loads in this case. We're just specifying that displacement of the end flange. So we're just going to set up our mesh. I'm going to use a curvature based mesh, and in this case I'm going to stick about 6 mil on there. That's a rough idea. I'm not going too fine, because obviously that's just going to take too long, and we don't really want to be sat here watching this solve while I'm doing the webinar. So there we go, you can see our mesh, and all we're left to do now is run. So I'm just going to hit run on there, and that should solve fairly quickly, because we are just using a shell mesh. The only solid components we've got are these end flanges, so this doesn't take too long to solve at all. If I remember rightly, I think it's about 35 seconds-ish, there or thereabouts. There we go, about 40. Okay, so now we've got our stresses. So what you'll immediately see on the right hand side is we've got our legend, which is telling us what the maximum and minimum stresses that are present. You'll see it's jumped up to a very, very high value. We've got 530 megapascals there, but you'll see that we haven't really got any red sections on the pipe. Instead, the red sections are what we're getting on the end flanges, where we've got that contact condition between the pipe and the end flange, and that's because we have got an edge to face contact. Finite element analysis doesn't really like contacts like that, because what we're doing in this case is bonding 2 bodies together just by an infinitely thin edge. Because we've got elements on that infinitely thin edge that can't move or have to move relative to the pipe, and we've got elements that are immediately adjacent to those that can move somewhat freely, we do get large spikes in the stress values, and these are what are referred to as singularities. So we would negate these. In actual fact, I'm going to show you how to concentrate on just the pipe in a moment. But the thing I want to show you really is the type of stress that we've got here. So what we've got is a von Mises stress. Now the von Mises stress is a scalar stress quantity. It's a stress magnitude at each individual point location. So these have been extrapolated across the surface, so that now we've got a smooth gradient. Now that's all well and good. That's what we would typically use to analyse. So the von Mises stress is generally the most widely accepted stress value from finite element analysis for solid, blocky, prismatic geometries, but that's not exactly what we've got here. And in actual fact, if you recall the stress requirements that we had from our ASME code or from any of the other codes, we're talking about longitudinal stress, not just scalar stress or stress magnitude. So what we need to do is try and focus now on how or what direction that stress is acting. So what I'm going to do now is just take a brief sidestep back to our model, and I'm going to generate a couple of reference axes. Now these are what I'm going to use in a short moment to analyze the stress in a longitudinal direction for these pipes. So what I've got here, first of all, is I've just grabbed the axis tool and just selecting the first straight section of pipe, and you can see with the yellow line that's going to stick an axis straight up the middle. So I'll hit OK, and I'm just going to call this guy number 1, so that's referring to pipe section 1. I'm also going to have to unsuppress my pipe body for just a moment so that I can grab some of these additional pieces of information for the pipe. Somewhere in here we should have my pipe outline. So I think it's, there we go. So I'm going to just quickly grab an axis and I would like to show that sketch for a second. He says let's bring those back on. So I'm just going to grab that point there for my first reference, and I'm going to use my front plane for my second reference. And so you see now we've got an axis for this case. So to analyze the elbow, I've got an axis that's going through the center of the radius, or the radius of curvature on that piece of pipe section. You'll see why that's important in just a moment. So let's hide those sketches again and make sure that, and then what I think we'll do, once we've just named this one 2, is stick one more on. So we'll just do this other straight pipe section. I don't think I need to keep repeating the same process, it's pretty clear what I'm doing now. So we've got those 3 axes in there. I'm going to suppress this guy again, just so that he's out of the way, and then we'll come back into our results, and so you can see we've got our stress just there. And instead what I'm going to do is take use of these, or make use of these axes that I've just created. So I'm going to define a new stress plot now, and I'm going to stick it in megapascals because our unit system is in megapascals. So it's handy if our results are just like that. It's pretty easy to compare. And then what I'm going to do is use the normal stress values. So in this case I'm going to use SZ, the Z normal stress, and I'm going to select for my reference this axis here. Okay, so what that's going to do is, because I've selected an axis as a reference, it's going to change my unit system into a set of cylindrical coordinates. So now the X normal stress value is going to represent the radial stress, so the stress in the radial direction from that axis. The Y value represents the circumferential stress, so, or rather a membrane stress, and or hoop stress rather, and finally the Z normal stress component represents the axial stress, or the stress in this case in the longitudinal direction for this straight section of pipe. So I'm going to hit the green tick now, and now that's allowing us to analyze just the longitudinal stress on this first straight section of pipe. Now what we can do is, if we wanted to just concentrate on the pipe, I'm just going to hide the results for a second, and then I'm going to nominate to hide the 2 solid bodies. Okay, and then when I bring back to my stress results, I'm going to double click on the legend over here. This takes me into the chart options, and I'm going to make sure that SolidWorks is only showing me the minimum and maximum range on the shown parts. So now it's negating the stress values on the flanges. So now the maximum and minimum stress values that are present on the legend over here represent the maximum and minimum stress values on the pipe section, and only the pipe section. Okay? And I'm going to do exactly the same thing following on. So define a new stress plot. In this case, I'm going to go with the Y normal stress. So this is the circumferential direction with respect to the axis. And because I'm grabbing this axis now, that's going to give me the longitudinal stress in this first elbow. So this is going to be the stress in section 2. Like so. So now we can have a look at the stress in this elbow. Okay? And we can go on. So I'll do just the one more because we did generate that axis. So I'll take my Z normal stress, megapascals, and I'm going to use axis 3 as my reference, and then we've got the stress values that are present in axis 3 on pipe section 3, sorry. Okay, the next thing we can do to try and gather some more intelligence from our results, I'm just going to hide these symbols as well so they're out of the way, is start using the probe tool. So if I switch back to my first stress plot, so this is the stress plot for pipe section 1, and right click on here and come into the probe tool. What I can now start doing is selecting areas of the pipe. In fact, what I might do is just go around it a bit so that we can start seeing how the stress varies as we go around the outside of that pipe section. Okay. I think we can probably stop around there. So here in the results we've got on the left hand side, we can see the maximum stress value of 68.5 megapascals in this section. The minimum we've got minus 54.7, so that's a compressive stress on the underside by the looks of things. We've got the average stress across here, and then we've got the stress on each of the individual nodes, so these are the locations that I just selected. If I hit this button here, SolidWorks will output that graph for us. So this is the variation of the stress as we go around that section that I've just selected. So each of these was one mouse click for each of the nodes. And we can additionally add a sensor based on these particular node selections. So if I save that like so and hit the green tick, you'll see that in my sensors folder now, up the top, I've got a workflow sensitive sensor, and that's going to allow me to use those exact same selections in another study. So I can just pick up exactly the same locations and see what the stresses are as a result of a different particular load scenario. Alright, finally I've got one more little tip, or one more little tool that we can use to get a bit more information, or a bit more accurate information from our stress results, and that's that's done by splitting the face. So in this case I'm going to split the face between halfway along this pipe here. So first of all, what I'm going to do is create a new plane, and I'm going to use my right plane. No, I'm not. I'm going to use my top plane even, and I'm going to just bring that somewhere over here so that it cuts roughly halfway-ish through the pipe section that I've got there. So this is section 1. And then what I'm going to do is edit the part that I've got just here. So this is again my surface pipe, and I'm going to insert a split line. And my target body is this body, and I'm going to intersect it with plane 1. Sorry, I've done that the wrong way around. Like so. So now you see we've got two selectable faces. So we haven't cut the pipe in half. All we've done is allowed two selectable faces, or rather given us a selectable edge halfway along that section. So now if we come back to our results, have a look at the stress in the stress in the Z direction on pipe section 1. So this is the longitudinal stress in section 1. What we can now do, as you can see, is grab that edge. So then if I come into my probe tool again, I can use instead the on selected entities option and pick up that edge, ask SolidWorks to update, and now SolidWorks will just run all the way around that edge and pick up every single node that's used to make up the edge that we've selected there. So now you can see we've got similar values, so I did alright in selecting it manually the first time, but you can see we've got a much smoother curve now because we are including much or many more nodes as we go around there. And that's obviously something that we can then pick up in subsequent studies. So we can use exactly the same split line to get the same location information from each of the different load scenarios. Okay. Finally, what I'm going to do is go through and start analysing some different scenarios now. So what I'm going to first of all do is right mouse button on my displacement study and just duplicate this. In this case I'm going to call this study force. So you see now we've got exactly the same study setup, but in this case we've got a new study and it's called force. What I'm going to do is delete that first fixture, and then I'm going to edit my fixed hinge. I might actually need the flanges visible again for the time being. I'm going to edit my fixed hinge and just make sure that I'm also constraining the 4 holes that we've got up the top here. So now we're assuming that these guys are fixed, and we're instead just going to apply a force to all of the pipe sections. In reality, we'd probably split the line, faces again, so that we've got one face, so one half of the pipe to apply the load to. A wind load obviously wouldn't act on all sides of the pipe. I'm just doing this to save time. Then what I'm going to do is stick, let's say, 200 newtons on the side there, and I'm going to, in this case, do the selected direction option, grab my front plane, and again stick my 200 newtons in here, so you can see the arrows are representing the direction in which we are loading here. So we've got a wind force pushing against the pipe in this direction. We hit OK, and now you see we are good to go again. So that's, the mesh is already set up, we've already specified that, we've already got our fixture and our force, our contacts are already set up. So now you can see we can very quickly start appending to our set of studies. And so that's that one good to go. What we can then go ahead and do is duplicate that again. So let's call this one gravity. And instead here I'm going to remove that force loading. I'm just going to apply gravity. What we do need to make sure we're doing is specifying the direction of the gravity. So you see the gravitational force isn't acting in the orientation that I'm after. So I'm just going to grab a different orientation, make sure it's going in the downward direction, and we've got the gravity study ready to go also. We can then go ahead and start combining each of these. So once we've got that, we could go ahead and start adding pressure loads on the inside of the pipe. We could go ahead and add a temperature load, so we could apply a bulk thermal change. So let's actually do that one. Let's go thermal, and instead of my gravity loading, I'm going to apply a temperature load. And so I'm going to grab all of the pipe here, and so SolidWorks is going to use the thermal expansion coefficient. I'm going to specify a temperature, so let's jump it up to 90 degrees C, and SolidWorks will use the thermal expansion coefficient to calculate the displacement, so that, and the resulting stresses as a result of the temperature, this temperature change on the solid body, or on the pipe body in this case, so the shell body. Okay, and that's that one good to go as well. And then what we can start doing is combining these. So let's say, for example, we had on our criteria pressure and weight. I haven't created a pressure study. Let's do a pressure study quickly. It's very easy. So we'll stick pressure on here. Let's delete that gravity. So we've got an independent pressure study also. I'm going to grab each of these individual faces, and we can see from the arrows that it's going inwards at the moment, so we want it going in the outwards direction. I can see the tips of the arrows pointing out here. Let's stick Let's go with the PSI value, I don't know, let's go with 40 PSI on the inside there, and OK. And so now you see we've got a pressure value set up. So then all we need to do is start combining these. So I'm going to duplicate that one, and let's call this pressure and gravity. And so we've got the pressure study, or copy of the pressure study, and all we need to do to bring these other values in is drag that gravity onto my pressure study, and you see we've now got pressure and gravity for this one. Likewise, we can also duplicate this one. Let's go with pressure, gravity and thermal. And so now we've got the pressure and the gravity there, so all I want to do is drag that thermal temperature change over onto this study, and you see we've now got all three results on there. And it really is as simple as that. The other thing that I did forget to mention that I will point out is another tool that's really handy in your post-processing. If I right click on my results folder over here and list the resultant forces, what I can do is select the 4 fixtures. So this is for my displacement study where we applied that displacement to these 4 bolt holes over here. If I hit update, you'll see what SolidWorks is going to do is calculate the stress, the resultant force, or the force required, in this case the reaction force, to generate that particular displacement. So you see we've got a magnitude here of about 5,516 newtons, and that's 5,110 in the y direction and 2,075 in the x direction, signified by these arrows. So that's another handy tool just to bring to your attention, and I think that is probably about all there is. So do join us again. I've got webinars coming up soon, rendering images in PhotoView 360, so that'll be the next one. That's next week, same time, then followed by multi-body modeling and installing with administration images. So as always, this webinar has been recorded, so it should be available on our website very, very soon. If you do want to get in touch, if you've got any questions, you can drop by our website, which is www.innova-systems.co.uk. You can email us to the support team at support@innova-systems.co.uk, or you can give us a phone call on the number that you see on your screen now. Okay, thanks for joining.